Dear students, in this video, we are going to discuss about current density. Current density is denoted by J. What is the difference between current and current density? Current means flow of charges per unit time through a conductor, whereas current density is something that tells us the flow of current per unit area. Okay, so that is current density. So here I would like to remove your misconceptions about the concept of current density. First of all, the name current density suggests you that it has to do something with volume of the conductor, whereas it has nothing to do with the volume of the conductor. Rather, it deals with the area, like how much current, how much charge is flowing through a particular area. Okay, and then you need to know that current density is a point function. Point function means it is always defined around a point. For example, if charges are flowing, if charges are flowing through some conductor, then if you want to know the current density around this particular point, like how dense the current was, how much the flow of charges was happening there, what amount was actually present there. So that is all which tells you about current density. So it's a point function. Just have a look here. Suppose there are many charges that are flowing. Now, if you want to know the value of current, then current would mean how much charge is flowing per unit time. So to find out current, we will consider a cross-sectional area and then we'll see that per unit time how much charge is flowing. And that is how we will get to know about the value of current. But it's not the case with current density. For current density, you have the same thing. Charges are flowing. You consider the cross-sectional area, but you need to see that around this point, at this point, what was the density of current? Okay, so what we will do? We will consider a very small area element around this point. Since we need to see the amount of charges flowing through, so that area will be enclosing this point in which we are very, very interested. So we'll consider a very small, infinitesimal area around this point P, at which we want to know current density. Okay, since physics considers area as a vector quantity in flux problems, and we know that area is considered as a vector quantity and its direction is taken to be the direction of the outward drawn normal on that area. So in that way, if you consider an area around point P and the direction of this area will be here, the direction of the current. Actually, current is a scalar quantity, the direction of flow of positive charges. So this is the direction of area. So that way we will try to find out कि जो point P के around जो infinitesimal area आपने consider किया उसमें कितना current flow किया, that will tell you the current density at this point P. Because if you are considering current density at a single point P, you need to see a very, very small area around that point. And then you need to check how many charges are flowing per unit area around that point. That will give you current density. So basically current density is equal to di by dA. where di refers to the small amount of current flowing through this area dA. So this is the case when we are finding current density at a point. But suppose, in case, if you have such a conductor at every point of which the current density is same, the current is flowing uniformly there. The current is not non-uniform. Okay, the current is flowing uniformly. Like if 5 charge carriers are passing through this point, the other 5 charge carriers are passing through some other point. So you are understanding. So current is flowing uniformly. If in that case, the value of current will be same. And in that case, we will not be writing J is equal to di by dA. Rather, we will be writing J is equal to I by A. And I is current, which is the same through every point of the conductor. And area is the cross-sectional area. But since the current is equal to charge upon time, so we'll write it charge upon time upon area simply as A. Now, you should realize one thing, that this is just the magnitude of current density, current per unit area, but it has got the direction also. Why? Because it is associated with area. Area is a vector quantity. Okay, we define current density around at a point, but see, since we need to consider a very small area around that point, and area is a vector quantity, so current density also is a vector quantity, and its direction is along the direction of motion of positive charges. So this is the magnitude. So we'll be writing direction also. We know that every vector, A vector, is written as magnitude into direction, A cap. So similarly, J vector will be written as magnitude, which is equal to di by dA, in case if the current is not uniformly flowing. So that will be di by dA. Direction is n cap, the direction of outward drawn normal from that area. You got it? So now, very important thing. So this was the case when you saw that the flow of current and the area are sharing 90-degree angle to each other. Right? But in case if the area is oriented in some different way, okay, area is oriented like this, then what will happen? So I'll tell you something. Just suppose you have an area over here. If this area is kept like this, vertically straight, there are lines that are passing through this area. Electric field lines that are passing through this area. But if you will tilt this area, few lines will go above, few lines will go below from it, and then eventually what will you see? That the number of lines that were actually passing earlier is not the same as the number of lines, electric field lines, that are passing just now. So orientation of area also matters a lot. So here, suppose the area is oriented like this, and this is the flow of positive charges, right? Now this was the original area. Okay, now the area is tilted. This dotted pink line is showing you the earlier orientation, and now it has been oriented like this. So just see the angle made between area vector and the flow of current. We know that area vector has the direction as outward drawn normal. So this is a tilted area. So it's just give me a second. This is a tilted area now, like this. So its outward drawn normal will be like this, something. Same here. This is the outward drawn normal. It's a tilted area. See the angle between area vector and the current, the flow of current. Suppose that is theta. So the component of area which is along the flow of current, जिसमें से actually में current pass कर रहा होगा, that will be a cos theta. You can resolve the vectors, and current density is equal to current upon area through which the current is actually passing. So that will be J is equal to I upon AN. AN is equal to A cos theta. I'll put it here. And that is how, see, keep the current over here and take this value over here. Current I will be equal to JA cos theta. And current will be equal to J vector dot A vector. Because current density is a vector quantity, area is a vector quantity, so the current is the dot product of both of them. This is otherwise also the expression for dot product of two vectors. So this is how we prove that current is a scalar quantity, and remember that current density is a vector quantity. So the next target is to establish a relation between current density and drift velocity. So this is the relation between current density and drift velocity. We know that current is given by NEAVD. Okay, N number density, E charge on one electron, A area of cross section, VD drift velocity. So current density will be equal to current upon area. So NEAVD upon A, that will give you NEVD. So this is the expression which relates current density and drift velocity of electrons. Fine. And we need to see what is the SI unit of current density. Okay. We know that current density is given by current upon area. Current is measured in amperes. Area is measured in meter squares. So ampere per meter square is the SI unit of current density. You got it? So next term we are going to discuss here is conductance. Conductance is exactly the opposite of resistance. Resistance means the capability of a material to obstruct the flow of charge carriers, to cause a hindrance in the flow of charge carriers. So that is resistance. But conductance is the reciprocal of resistance. It is actually the ease with which the charge carriers flow in a conductor. Conductance is denoted by G, and G is equals to 1 upon R, or its units will be 1 upon ohms. Okay, so we do write ohm inverse. Ohm inverse is also known as Simon. So this is the SI unit of conductance. After that, we'll be studying electrical conductivity. Electrical conductivity is represented by the symbol sigma, and this sigma is opposite of resistivity. This sigma is opposite of resistivity. Remember resistivity, which is denoted by rho, and I told you that since resistance is directly proportional to the length of the conductor, more the length of the conductor, more hindrance the charge carriers will face to flow through a conductor, so more will be the resistance. So resistance is directly proportional to length of the conductor and inversely proportional to area of the conductor. And when you will replace this sign of proportionality with equality, there will be a constant, and that constant was equal to rho, if you remember it. And then I told you that rho is nothing but it is resistance only. बट ये वो रेजिस्टेंस है, उस मटेरियल का रेजिस्टेंस है जिसका लेंथ आपने 1 मीटर कंसीडर किया और एरिया आपने 1 मीटर स्क्वायर कंसीडर करके रेजिस्टेंस फाइंड आउट करने को ट्राई किया. So that is resistivity. It is basically equal to resistance of a material whose length is taken as 1 meters and area is taken as 1 meter square. So conductivity is exactly opposite of resistivity. So basically conductivity is 1 upon rho. Conductivity is 1 upon rho. Remember that. And one more thing, if resistivity is nothing but resistance of 1 meter length of a conductor and 1 meter square area of a conductor. Similarly, conductivity is nothing but conductance. Conductivity means ease with which the charge carriers are moving. But for finding out the conductivity, we, restrict our parameters to 1 meter length and 1 meter square area. Anyway, so rho is basically RA upon L. R is measured in ohms, area is measured in meter squares, and length is measured in meters. So ohm meter is the unit of resistivity. So what will be the SI unit of conductivity? It will be 1 upon ohm meter. Ohm inverse, meter inverse. But just now I told you that ohm inverse is nothing but Simon. Simon meter inverse. S meter inverse is the unit of conductivity, or simply you can write it as ohm inverse, meter inverse. Clear? So this is all about conductivity, conductance, and everything about the current density.